Hey students, I got a request to help out on number 65 from the harder book. It's in our chapter 22 of our college physics book, but jumping into the calculus one, or the advanced book, this one really isn't a calculus one, but it's a prep for the next one, which does involve calculus. But this number 65 looks like this. I printed it up here, and it says that you have three straight parallel wires and carry a current of 10 amps. They are positioned and shown in the accompanying figure. What is the magnitude of the magnetic field at point P? Now, I don't know if you can see it real clearly, but there is a blue dot and a blue X and a blue X here. And they're trying to show then currents coming, what would be in and out of the screen. The X means going into the screen. So maybe it would work better if I held my pen here to get a visual picture and pointed my pen down into the screen. This is what they're trying to show, is that the current would be going into the screen, or in my case, into the paper, and it would be 20 amps. And then the same thing in this corner here. So I'll put another pin right here. And so both of these are going in. And then the third one is coming out. So maybe I'll point the pin up in towards the screen here. And see if I can even hold all three into place. Other than my fingers are kind of blocking the view of the pens. Hopefully you can kind of see this in 3 dimensions, because that could be part of the challenge at the beginning, is just get a visual picture of the 3 dimensions. Okay, so this one here, which is my green pen, is into the paper or screen. This one, which is the red, is into, and this one is out of. And we're trying to see the magnetic field at point P. Well, before we dive too deeply into this problem, let's go to your textbook here and kind of look at this section. I forget it's definitely chapter 22, and it's this equation, equation number 26. And it gives us this is the wrong one. This is the magnetic field of a loop. In fact, it even says a loop. My bad. Okay, so I don't want this one. I don't have a loop. Sorry, it looks like I printed up the wrong one. But I do have the long wire. And so let me just write the correct equation. It's permeability of free space times current over 2 pi r. And maybe I'll check your author here. If he uses a capital R, he uses a lowercase r. Okay. And it's equation 22.24. I'm looking on the screen right here. So, forgive my mistake of printing up the wrong one. This is for a loop. It even says center of loop. But this then is for a wire, and that's what these pictures are for. Okay? And so if you got a moment, go back to this section. In fact, as long as I have the book up here. It's actually just before this one here, and I guess it's in section 22.9, where it says magnetic field produced by Ampere's law. But that's what I'm going to do for this problem. This gives me the magnetic field from one wire, and you can see in this problem I have 3 wires. And so basically I'm just going to take this information that they give me and worked out on the magnetic field from a single wire and do it 3 times. Now I suppose we should talk a little bit about this single wire. This is how you calculate the magnitude of the field. You get the direction from what your author calls right-hand rule number 2. And he says if you have this wire, and so in this picture he's got the wire pointing upward, and the magnetic fields are these rings around it. And so you can see by the equation for a given distance r, let me just kind of draw an r here, and so the magnetic field on this outer ring would all have the same strength because it's all the same distance from the wire. That's what the r means. And so in our problem, we're going to have a current of 20 amps, and we're going to be some distance away, which we need to think about. But along this circle, it would all have the same strength given by this equation. And to get its direction, well, since it's a circle, it either points clockwise or counterclockwise. And the easiest way to kind of figure out which of the two it is by using what's called right-hand rule number 2. You kind of imagine yourself grabbing the wire with your right hand, and your thumb is extended in the direction of the current. And so as you look at what I call the thumbs up position, you will see how your fingers kind of curl around, and your fingers, if you kind of think of the tips of your fingers as a pointer, then the curl of your finger curling around is pointing in the same direction as the field. You see, if I were to grab the wire incorrectly like this, my fingers would be curling around the other direction, and it would be opposite of the direction of the field. So you don't want to grab it wrong, and you don't want to grab it with your left hand. You need to grab it with your right hand, with your thumb in the direction of the current, and then you could just look at your fingers. Okay, so assuming you already know all that, now we can jump into the problem, because we have both a calculation based upon what is the strength of the field, and in addition to that, what direction is it? So maybe I will start with this one here. Let's just look at this one here. Now remember, this was supposed to represent the current of 10 amps coming out towards the screen. So maybe if I start with direction, I would imagine grabbing this with my right hand, with my thumb in the direction of the current. And as I look at my fingers, they would curl around in a counterclockwise direction. Okay. Now, I'm not interested in the field everywhere in space. I'm only interested at point P. And so if I were to draw the magnetic field at point P from this 20 amps, it would be like this. It would be tangential to the circle. And this distance here is that radius. And so maybe I'll call that B1, the field from number 1. Now, as long as I'm working with direction, maybe I should look at the direction of the other ones also. So if I come over here to this corner one here, the lower left-hand corner, I guess, and remember that this is representing the current going in. Okay, and so if I imagine grabbing the wire here with my right hand, thumb pointing down, and maybe it's hard to see, but I'll turn it over so you can see. Okay, so I'm grabbing the wire with my thumb pointing down. This would make then a magnetic field going around in a clockwise direction, like this. And at point P, it would be angled something like this. Maybe I'll call that field number 2. And then the last one, again, pointing in. And imagine grabbing it with my right hand again. So again, it's kind of hard to see my thumb, but I'll turn it over here. My thumb is pointing down. Okay, so pointing down. I would have a magnetic field making these circles around it. Now again, I'm not interested in the field everywhere, so I'm not going to draw a big circle around it like I did here. I'm just going to draw the direction of the field at point P. And so this big circle would go around, and tangential to the circle would be right here. And so let me call that field number 3. Whoops, 3. So these are the fields, and let me just kind of double check. So this one would be up, and so it would go down at that angle. This one would go down, so it would be off at this angle. And this one would be down, so it would curve around and go kind of horizontally left. Okay, good. So these are the 3 fields, and I've got to add them together. Now, the good news here is that these are all the same length in magnitude. Because the equation is mu naught I over 2 pi r. And like I said, the way this is set up, you can kind of see we have 10 centimeters, 10 centimeters, and 10 centimeters. So this is an equilateral, which also means equal angular triangle. And they all have the same current. So this point P is the same distance from the same amount of current, so the magnitudes of number 1, number 2, and number 3 are all the same. So I can just say magnitude of 1, magnitude of 2, and magnitude of 3 are all the same. In fact, maybe I should calculate it while I'm here. The hard part might be getting the distance, and so maybe I will look right here. But I'll use a little trigonometry for that. Starting with geometry, I know that this is an equilateral triangle because of the 10, 10, and 10. So it's also equal angular. So I know this whole angle here is 60, and the one involving this triangle is 30 degrees. And then this one splitting down the middle makes this length 10 centimeters. Now maybe I need to prove that a little bit, but this one says you draw down the center and hit it at 90 degrees, which would mean this would hit at 90 degrees, which would also mean that is 30 degrees. And so I didn't want to make too much of a mess here, but this triangle here then in blue, and this triangle here in green would have a side that they share, and they have an angle that matches another angle. So this is angle side angle congruency. Congruency means they have the same angles and same length, so that means this length here equals this length here, and the total's 10, so this has to be 5 and 5. So I guess that would be the more formal argument of why this has to cut in half and give me a 5. So keeping that in mind, I can say cosine of 30 degrees. So looking at this angle would be 5 over this distance. And this is the hypotenuse of this triangle, but it's also this r, this distance, that point P is from the 20 amps. So I'll just call it r. And then doing a little math, r then becomes 5 over cosine of 30. Which is that root 3 over 2. I guess, actually, now that I think about it, this is also one of those common triangles. It's the 30, 60, 90 degree triangle. But maybe I'll just do the, let me check my mode here. Am I in degrees? Okay, good. But this cosine 30 is the, it doesn't give it as a root 3 over 2. But if you wanted to remember that, you could go root 3, oops, messed that up, root 3 divided by 2. And so there's geometry or trigonometry gets you to the same location. But anyway, let me divide 5 by the cosine of 30. That's probably just the easiest way, not to try to remember root 3 over 2. although you still have to remember your trigonometry. But my point is, we're looking at a distance of about 5.77 centimeters, and probably should convert that into meters. So 0.0577 is my R value. And so knowing that, I can now get the magnitude of each of them. The mu naught is the 4 pi times 10 to the minus 7. The current is 20 amps. The 2 pi is nice to leave as 2 pi so that I can cancel a little bit with the 4 pi. And then the distance R is the 0.0577. All right, so putting this into my calculator, in the top I'm going to have 2 times 10 to the negative 7 and multiply it by 20. Then I'll divide it by, and I already canceled off the 2 pi to make that a 2 there. So I will then just divide by 0.0577. And this comes out then to be 6.93 times 10 to the minus 5 in units of Tesla. And so there's the magnitude of the magnetic field. And that, I guess, relatively straightforward. I mean, we're just going to take an equation out of the book, and then we're going to plug it in. We do got to do a little geometry or trigonometry, maybe a little bit of both, in order to get the R, but this is the magnetic field. Now, still a challenging part of this problem is to add all these components together here. And so let me just kind of draw them by themselves. This is the one I call B1 right here. Let me put a vertical line to kind of help me remember what is vertical. And then this is what I call B2. Now maybe I'll pause there before I put B3 on here, because these two angles, I'm pretty sure, are equal. And that would be nice if they were. So let me prove that, because if they are, what that would mean is the components in the x direction for number 1 and the x direction for number 2 are going to cancel each other. And I then even don't have to think about it, don't even have to worry about it. And also, it would mean that the vertical component of number 1 and number 2 are the same. So I just have to do the downward vertical component of number 1 and double it, and to get the combination of those two. And so I think I need to do something along these lines. Maybe it'll stand out if I do a different color. Oh, black nearby. Is this a black? Oh, this one's busted. Guess that's not going to help. Oh, bummer. I used to have a black one. Lost it somewhere. All right, well, can't find my black one at the moment. Let's see if I can actually find a black one in these colored ones. Aha. Ooh, all right. Yeah, okay. Never used the black one out of the color markers. I just use a regular black ink. All right. So this is, well, I don't know if this will stand out because maybe that was a bad choice. Anyways, but I do want to say, kind of like we said 30 degrees is here, we could argue that this one down here is also 30 degrees, making this angle right there 60 degrees. And so given that this, from our right-hand rule is tangential, oh, I'm sorry, I'm looking at the wrong one. Given that this one right here is tangential, so it goes like that, this whole angle has to be 90 degrees, and if that is then 60 degrees, it leaves 30 degrees from the vertical. And that's what I'm trying to get at. I'm trying to show that that angle is 30 degrees. Because I do believe that for number 2, we're going to have that same argument here. So let's take a look at the direction of number 2. And again, I'll take my right hand and then point out that then this one has to be perpendicular to this distance out, and that this part of the triangle has to be 60, so this vertical piece must be 30. And that's what I needed to prove to convince you. If I write number 1 in its components, you could think of it as a down piece and an over piece. Okay? And so just looking at 1 and 2, I guess if you wrote it this way, the x component of number 1 and the x component of number 2 are going to be 0. So that'll save us a little bit of work and headache trying to work out what is the x component and then combining them together. Those just go away. And I think the best part then is the total field, we'll call it B total, is all in the y direction. And it's twice the y component of number 1. And you would get the y component by taking the whole field, number 1, and multiplying it by cosine of 30 degrees. And so what I would have so far with just 1 and 2 combined together, putting in this 6.93 times 10 to the negative 7 Teslas, okay, from our earlier calculation. And then another root 3 over 2. I'll get, let's see if that's still in my calculator. Okay, that number's still there, so I will double it and then multiply it by cosine of 30. So this is 1.20 times 10 to the minus 4. Okay, so that's what I get when I have just those two. Okay, and so maybe I shouldn't use the word total because it's not the total of all 3 yet. I've only done 2 of them. But I wanted to do those 2 because, like I said, I kind of suspected something nice would happen here looking at the symmetry of the geometry. So I don't have to worry about an x. I only have a y. And that is doubly helpful because now if you look at number 3, what you see when you do this right-hand rule is number 3 is all in the x direction. So adding it to my diagram, number 3 is all x. And so if I take the result of 1 and 2, which is all y, and then combine it with number 3, which is all x, I essentially have something that looks like this. All y plus all x. And that means the total is just Pythagorean's theorem, taking the y component and squaring it, and the x component and squaring it will get you the square of the hypotenuse. So my complete total field of 1, 2, and 3 squared would be this y component squared, 1.20 times 10 to the minus 4 squared, and x component, which is only number 3, now that 1 and 2 x components canceled off. And remember, number 3 has this magnitude also, so this would be 6.93 times 10 to the minus 5, and I'll square it. And so grabbing my calculator, looks like I guess I still have this number in here. So let me just hit the square and add to it 6.93 times 10 to the negative 5 and square it. And so that'll be b squared. And so finally, let me take the square roots, and we're looking at 1.39 times 10 to the negative 4 Teslas. I know I didn't put the units in there, but that's the unit for the magnetic field. If I use meters for distance and current in amps, and I did. Anyways, and so that would be the magnitude of it. Now, we could get the direction, but I don't think they asked for that. Let's see. What is the magnitude of the magnetic field at point P? So I think we got it. We don't have to do a little bit of inverse trig to figure out the direction. Although that wouldn't be hard, because if this is angle theta, we would have the tangent of theta, and it would be this x component. So it'd be the 6.93 times 10 to the minus 5 over this y component, 1.3, y component, 1.20 times 10 to the minus 4. And I'll stop there, but you can then solve the math to get the angle had they asked for both the magnitude and the direction. All right. Hope that helps. Take care.